lambda cos square of theta 0. So if I give you this expression, and we have in mind that lambda was kind of h bar, this is classical, and this should be kind of semi-classical. Logs of h bar, typically, if one goes to Coleman book, he says, okay, if you have a log of h bar, this is something that is related to some zero mode, and this order 1 in lambda number should be captured by the perturbations computing determinants over the surface I am which expanding on. This is what is said here. We have square root of lambda. Log lambda will come from zero modes. We are having a disk-like surface. The number of zero modes on this surface has a topological nature. This can be computed from topological arguments. In the disk, it can be seen that it is 3. So in principle, this, if you take out this 1/2 here, you have a 3/4. And these 3/4 could be understood, Drucker and Gross conjecture that it should be related to the 3 conformal Killing vectors that appear upon fixing all the action, because we have to do this, and when we have the metric, we have to fix the diffeomorphism invariance. You go to Polchinski chapter book, you put the Fayet-Popov, and this Fayet-Popov should have 3 zero modes. To avoid this discussion, what we typically do is to compare the latitude to the 1/2 supersymmetric, and in doing this, these logs cancel, so we don't pay attention to them. And we end up with 2 pieces. One is the leading piece, the other one is a subleading. This is leading in big lambda. This should be captured by the classical surface, and this should be reproduced by computing determinants. Okay, generically, what are we doing? We are taking this string action and expanding around the surface, looking for a classical solution, perturbing, obtaining a quadratic fluctuation over the surface, and computing the determinants of these fluctuations. We want to do this. So we will have some normalization, the classical action, and the determinants of the bosonic fermionic fluctuations. And if we were working in the Polyakov description, we had to fix the Fayet-Popov of the diffeos. This is what I say here. Good. So let's go to the solution. We are looking at a solution which will be the 1/4 BPS Wilson loop, which will be a circle on the geometric space, a circle on the internal space, and we want to have a surface which enters into the bulk and caps on the 5 sphere. Well, to do this, we have to find a nice coordinate system on which to write the metric of the spaces, pick an ansatz, solve for the ansatz. This was done long ago, and place the boundary conditions. This is the final outcome. We can write ADS in this particular coordinate system, foliated in this way. Place this u equals 0, and you end up with a non-trivial profile for the embedding of the surface inside the internal space, and u is equal to 0, and we cover a kind of ADS2 space inside ADS5. In this procedure, we have to fix, since theta is changing when we go from the boundary into the bulk, this is set to be a constant, and we have to say, we have to fix the parameters, the position on the 3 sphere which we are sitting on this along this curve. This will turn out to be important later. What does the induced geometry look like when we do this? The geometry looks like asymptotically ADS. So we can write when we pull back this surface onto this metric, we end up with this induced metric on the string surface, which is ADS2 times a conformal factor. The conformal factor goes to 1 at infinity, so it's just a deformation of ADS. If we, instead of working with a general latitude solution, we place our n to be constant all along the curve, which means turning this theta 0 to be 0. So it will be a constant all along the way. In that case, this is 0, and the metric is exactly ADS2. So the 1/2 BPS Wilson loop has an induced metric, which is pure ADS, Euclidean ADS. The geometries we are obtaining, which are smooth disk-like geometries, one can explicitly see that this has 3 conformal Killing vectors. In the case of theta 0 equal to 0, these 3 conformal Killing vectors are just the 3 isometries of ADS2, so in particular in that case they are Killing vectors. We can now compute the on-shell action. The on-shell action has to be regularized. This is very well understood, and we end up making a Legendre transform to take into account for the proper boundary conditions, cancels the divergent terms, and we end up with a finite action which easily reproduces the expected result. This is what we were willing to obtain. This should be the leading, would be the classic. This is obtained in this procedure by finding this surface, evaluating the on-shell action, and we end up with the same result. Okay, so this is what I said. There are important limits when we take this theta going to the North Pole. We are in the 1/2 BPS. In this case, we end up with a pure ADS. M is equal to 1. We can compute the Killing vectors. The Killing vectors have this form. They, as you can see, this is asymmetry, but they move on the boundary. Okay. And there's another particular situation, which I will not be discussing, but Kostya possibly tomorrow will be talking about, which is the theta 0 when we place the string such that this theta is on the equator of the surface or on the internal sphere. When we do this, notice that if we add the boundary, because this circle here, the circle at the latitude position, is the position of the circle at the boundary. So when we place this circle on the equator at the boundary, and we say theta 0 is equal to pi over 2, this cosine vanishes. The position on the sphere, on the complementary 3 sphere, is absent from the boundary point of view, and this hints to the appearance of additional zero modes for the solution. This is what I'm saying here for the 1/4 BPS, and these exceptional zero modes. Well, this kind of Wilson loops, for which theta is equal to pi over 2, are called equatorial, and well, Kostya may talk about them, possibly. So now we want to make fluctuations and compute determinants. What should we do? Take the string, fluctuate, fix all the gauges you need, find the second order differential operators, and try to compute their determinants. How are we going to do this? This could be done, okay, at the quadratic level. We could choose between working with Nambu-Goto or Polyakov action. I will be talking about Nambu-Goto, which is the work we did. There's an Italian group which worked in this Polyakov description. So let's do it. Well, I will not do it because it's long and there are a lot of expressions. Say you fluctuate and you end up with the second order operators. Now what I want to do is to compute the determinants. How do I compute the determinants? See? When computing the determinants, I will come to that. It's the important question. Okay? See? Good question. As Okudu is saying, so now we want to compute the determinant. The determinant is completely determined. The value you will obtain for the determinant will depend on which boundary conditions you impose on it. This will depend on which coordinate, on which set of coordinates I use to compute and try to argue which are the appropriate boundary conditions. Good. So this is what is said here. If we want to compute determinants, we need a differential operator, boundary conditions, and an inner product. Okay? In the sense that we have to define, I may compute a fluctuation, and if I compute a fluctuation, typically we write it this way, but nobody prevents me from saying that I put an m here, I divide by an m, and I put this as a new inner product. And I have to see how this depends on m or not. And this is crucial, and this is important in order to determine what are the normalizable fluctuations I will be talking about. So what is the idea of what I am going to do? What I'm going to do is to compute the determinants using a zeta function technique that I will mainly flash. And the idea would be to relate. So I want to compute the 1/4 BPS fluctuations. In order to compute this, I have already shown you that the induced metric for the 1/4 is conformal to ADS. So what I will do is strip away the conformal factor, which between the 1/4 and the 1/2, which turns the operator in a modified geometry onto a geometry which is pure ADS, and this will involve certain modifications of the operator, and compute the operator in ADS, and then using well-known theorems in 2 dimensions which relate determinants between different measures, when I take away or put these conformal factors, add the contribution from having extracted the conformal factor. So this m is always the same m. The 1/4 has this. I will compute the term. I will manage to manipulate and write down the operator, taking away this m. I will compute it without the m, and then I will add the contribution of having made this Weil transformation. This is a very well-known expression. Schwartz, it's something that we use all the time in 2 dimensions. You can see that this, for example, this expression is just a Liouville action when you write down m like e to the I5. Well, I have been very sketchy here. It's valid also. It has additional terms which involve the extrinsic curvature at the boundary, but you can see that all these terms cancel. This is for a closed surface. In this particular case, it involves it is known. In the presence of boundary, a full expression is known. This is in the paper of Drucker, Grossi, Zeitlin. You can find it there in the appendix. And in this particular case, when I am relating the conformal ADS to ADS, these boundary terms involve derivatives of m. M goes to 1 at the boundary. You can see that everything cancels. So, not very illuminating, but when you do the fluctuations, you end up with an effective one-loop action, which will involve fermionic operators. These are coming from the fermionic fluctuations, and these are the bosonic ones. Here you may see the expressions. You have masses for constant masses from some of the scalars. Here you have non-trivial potentials that end up being there. You find charged scalars. These A mu's that appear in the covariant derivative are inherited from the spin connection in 10. It has to do with the normal bundle. Bueno, here you have everything. Here is the dependence on theta 0. We want to compute these determinants. Will we be able to do this or not? I will now show you. This has been written down in a precise gauge, choosing a mu to collapse smoothly at the center of the disk. And you may see here that the fermion has chiral and non-chiral masses. When you go to the 1/2 BPS limit, this omega goes to 0, and you only end up with a single chiral mass. These are just generalizations of expressions that were found some time ago for the 1/2 BPS limit by Drucker-Gross and Kruczewski-Tirsiu. So this was the classical. We would like to reproduce this number by computing this. What can we do? Of course, any two-dimensional metric is conformally flat. So I can also take away this sine square outside, redefine rho, and I will have flat space times a new conformal factor. The difference with this is that in doing that, this was something that we did in previous papers, which is not what I'm going to comment now. But in doing this, we are changing the topology of the worldsheet surface. Essentially, what we are doing is that we are turning the disk into a cylinder. My viewpoint is that I will try to compute this in an honest way, trying to perform everything in the disk topology by performing a zeta function computation. This is okay. So what are these two perspectives? These two perspectives are, I will now comment on one. This is, take away the sine, you end up with this, forget about the omega, and then add the omega by looking at this, whether this gives you contributions or not. This is something that we developed. If you do this, you have a two-dimensional surface on a cylinder. It will be natural to decompose, and everything is, you can see here that everything depends, everything is circularly symmetric due to the geometry. So we can Fourier decompose. The idea of computing the determinants would be to decompose in each Fourier mode, and then sum over all the Fourier modes. And then for each Fourier mode, compute the determinant using the Gelfand-Yaglom technique, which involves solving for the homogeneous solution of the differential operator. This is something we did, and it didn't work. We ended up with the expected result and an additional piece. And Kostya will comment on this, how he managed to solve for this. So this was done in 2016. When we did this, we were worried, puzzled, sad. So we decided to attack the problem from a zeta function point of view. Zeta function, very well-known, elaborated technique. Was used in many papers in the 90s by Camporesi Gucci, Drucker-Grossi Zeitlin in its seminal paper where they developed all the techniques to compute fluctuations for the Wilson loop. Buchbinder and Zeitlin use the zeta, the heat kernel zeta for the determinants of the 1/2 and couldn't reproduce, but then the Italians, Valentina Forini, Arcadi, Eduardo Vescovi, made a computation performing, take the 1/4 and, why are you laughing? Take the 1/4, expanding theta, and work out the deformations of the 1/4 with respect to the 1/2 and perturb in theta and compute the determinants as deformations of the 1/2. They computed and they ended up finding an agreement with the result. So this was done in 2000, I don't remember, 17. So with this result, we said, okay, let's try to do it fully for any theta. In order to do that, we had this idea of mapping the deformed geometry to the pure ADS, and then adding back the anomaly provided by making this Weil rescaling. Maybe to Okuda's question, when computing this in the map of this picture I stole from Kostia's paper or his student PhD thesis, I guess. In mapping the disk to the cylinder, when in this particular topology, sigma equal to 0 is the boundary, and sigma equal to infinity is the center of the disk, if you pay attention to the coordinate transformations. So when I want to compute this determinant, I have to place boundary conditions at 0 and at R. Okay, so I will forget about this and compute on 0 and R. The expectation would be that when I compute these determinants, I have many determinants. I have determinants for bosons, for fermions. The expectation would be that this 0 is the boundary, so I will put an epsilon, and this R is the center of the disk, which in principle is not physical at all. So I would expect that irrespectively of the boundary conditions I put in R, everything depending on R will cancel, and the dependence of epsilon, I would expect that if supersymmetry is preserved, the dependence on the divergence due to the infinite volume of the space will cancel. This we show in our paper with Diego in 2016, that potential divergences in the Fourier sum cancel. This was appealing in the sense of cancellations of divergences, but it was not giving the correct result. Kostia solved this, and maybe he will talk about this tomorrow. So at that moment, we were happy with some of the, we were happy, middle happy. Not too much, not too little. So we decided to attack the problem in a different way. Is this conformal transformation? Notice that now, when I do this, and I strip away this conformal that is completely smooth, stripping away this conformal factor is not smooth at all because it diverges at R equals 0, so it is changing the topology. This I found it more kosher. Okay, so we wrote the operators on the deformed Wilson loop as Weil scaled to pure ADS. This involved corrections of the potential, you can do that. And now we compute the determinants as the determinant we want to compute is the determinant on ADS plus the anomaly piece arising from this Weil transformation. So how do we compute? This is, we computed in zeta function. Zeta function is a well-known technique. What is the idea of zeta? Bueno, again, since we have circular symmetry, we are going to decompose this in Fourier modes and add all the Fourier modes, but each of these we are going to compute via zeta function. And now Okuda's paper again, he will ask me, and what boundary conditions are you going to put? So now I'm going to tell. So we generalized some work that was done by Kirsten and Dun to ADS. They have done it in flat space. They didn't include gauge fields. We include gauge fields and analyze this problem. So typically in zeta function, you know that the determinant is given by the zeta prime, and eventually you may have a dependence on the scale given by the zeta of 0. Better be that in the end, when adding all the determinants of all the fluctuation, this term cancels, this can be seen, so the determinant has an intrinsic meaning independent of the scale. This is what is going to happen. So how does zeta function work? Zeta function goes this way, and this is how we compute it to end up with the final expression that we use to compute the determinant. So in principle, you define the zeta, which is 1 over lambda, all the eigenvalues to the s. You write down this as a contour integral. You have this, and you use Cauchy to write down this. You will be able to do this if you find a function such that it has zeros, such that it gives you residues at the precise position of the poles. So you pretend you know this f, you write it this way, you deform the contour, you go to the other side where this is the branch cut appearing because of the lambda to the s, you go to this side, you collapse, and you end up with this expression. This is the typical expression of the zeta function. So, okay, good, but what is f? Okay, I will show you what is f. We want to solve this with particular boundary conditions. In principle, we want to compute all these lambdas. This is unpractical. For a general operator, we will not be able to solve for all the lambdas. So instead of solving this problem, you go to, well, there are many places. You can go to also to Coleman, one of the appendix of Secrets of Symmetry, where he shows that instead of this, work this problem in the complex plane, try to look for lambda, and place boundary conditions. When I'm writing this, I am thinking of this x that I'm putting here as being the radial coordinate, so I am putting regularity at the origin, which is the only thing I will impose. It is clear from this expression that if I am able to solve this for any lambda, precisely the eigenvalues of the problem will be those such that if we are solving for Dirichlet in 0R, which means function has to be 0 here, 0 here. What is the value of lambda such that if I solve for this, it is 0 here and 0 here? Precisely solving for this, evaluating this u at big R, the eigenvalues are exactly the zeros of this function as a value of lambda. So this is the required f of lambda. So if you want to solve for the determinant, you only need to compute one function, which is this one. And now let me be brutal. This is not correct, but let me be brutal. I want to compute zeta prime. So zeta prime, I derive this. I will end up with a cosine, and then I will end up with some log of two terms. The cosine, when evaluated at 0, it will be 0, 0. This will be the log of this. And so the zeta prime will be just the log of this function evaluated at infinity and 0. And this term, disregard this term, assuming that everything is regular. If I do this, and now I compare some determinant to some other free determinant, and assume that this free determinant will be, in this case, comparing the quotient of determinants with respect to having no potential, this dependence on the function at infinity will blow away. And this f of 0 is nothing but the homogeneous solution. So this is a very naive way of looking or seeing how the Gelfand-Yaglom expression, this expression, which involves Gelfand-Yaglom being the homogeneous solution, can be obtained from a zeta function idea. Okay, I lied a lot because this has to be regularized. This can be done. So now we do it on ADS. We look for this function. We do the same trick. We do it, instead of do it in the energy plane, we do it in the momentum plane, K. We write the energy as 1/4 k squared. This is the typical eigenvalues in ADS geometry. We found this f K of L. This can be done. And then we regularize all this that I lied. You can regularize. The way to regularize some expression is to subtract the divergent piece at infinity. You subtract, you make it finite, and then you add it back. And when you add it back, you can easily analytically continue to s equal to 0, which is the typical zeta function technique. We end up with these expressions. And we found the expected result, but a reminder that is not 0. But we found an expression that coincides with our motivating starting point, which was Zeitlin, Forini, Vescovi, which was giving the correct result. So in fact, what we obtain is something that does not agree exactly to all order, but agrees with what was already known, but agrees at the first order. So I have 1 minute. So I was getting hurry because of this. Okay. So you see, this the situation we end up with was we computed the determinants. These determinants were are coinciding perturbatively to first order, but then they do not coincide, and this is something we are puzzled, and we will try to understand how to solve. So to finish, let me tell you, well, okay, what have we seen? We have seen that Wilson loops are dual to string with appropriate boundary conditions. The leading order matches. The subleading in this kind of computation doesn't agree. Kostya will tell tomorrow that he managed to solve these problems using another technique. But in all this, way I told you the story, I am putting under the rug many questions that we originally had when we started the problem, because we were willing to understand how the SUSY boundary conditions were implemented in the problem, and I never talked about this. All these computations assume that longitudinal and ghost determinants coming from the if you go to the Polyakov setup, you have the Fourier-Popov fixing determinant and the longitudinal modes, and these everybody cancels them, assuming that they cancel, but they are not computed they are not computed. One assumes that they cancel, although the determinants look identical, the operators, but the boundary conditions, the determinant could be the same, but the boundary conditions on each of these modes could be different, so it is not in principle. Assuming that they cancel, one could obtain a result, but it's not doing from first principles. This 3/4 argument, possibly Kostya will talk about tomorrow. He solved it, but this argument doesn't work for type 2 Wilson loops in ABJM, so it's not clear that how this argument works. And the zeta function, when applied, we also applied this to ABJM, and there are some subtleties because of the appearance of massless fermions, and then the zeta technique becomes subtle. Okay, and then there are issues about kappa symmetry. I mean, if you end up with a lot of assumptions ending up with a result, since we didn't obtain the precise result, we said, okay, maybe many of these assumptions we have to review them again. Okay, so this is it. Thank you.
Are there questions?